Okay. So, we come to this final lecture on microwave filter. So, here we will see some tutorial problems. We have seen a long journey. We have started from the image impedance concept and how based on image impedance the low frequency filters were designed. Then we have seen the this insertion loss based microwave filter design. In image impedances already we have introduced the concept to highlight their importance, but those problems generally you can solve yourself. Also in the tutorial sheets we will give some problems, but let us see the insertion loss based designs. And suppose if we want to have, let us say, maximally flat low pass filter is to be designed for cutoff frequency 8 gigahertz, minimum attenuation of 20 dB at 11 gigahertz. So, how many elements are required? Elements means how many inductance, capacitance, etc. each are elements, how many required. So, what is said that I require that minimum attenuation should be 20 dB and at what frequency? 11 gigahertz. So, what is your cutoff frequency is given as 8 gigahertz. It is a maximally flat filter, a low pass filter. So, what I am saying is this is my cutoff, this is my PLR, this is my omega c, but I am specifying at certain other omega, let us say 1, I am specifying that it should be at least this. So, you should achieve this is omega. So, let us see that what is said is what is omega c. Omega c is 2 pi into 8 into 10 to the power 10 hertz, 8 gigahertz. So, 10 to the power 9 hertz, and what we want that at omega is equal to omega 1, which is equal to 2 pi into 11 into 10 to the power 9 hertz, not hertz, omega cannot be hertz, omega is radian per second, this is also radian per second. I require that PLR should be 20 dB. So, basically this omega 1 by omega c, that ratio is nothing but 11 by r. We know that for Butterworth type of polynomial, this is a maximally flat, means it is actually Butterworth function we can use to synthesize. So, for omega greater than omega c, we know that PLR can be approximated as omega by omega c whole to the power 2n. That means that one term I can neglect. So, if I put it in dB, PLR dB, that will be 20 n log omega by or omega 1 by omega c. So, 11 by 8. So, you can solve for this, it is given as 20. So, 20 is equal, put it as 20. So, that gives you n is 7.23. Now, n needs to be an integer. Now, obviously, it says at least 20 dB. So, if I take n is equal to 7, it won't be at least 20 dB. So, I know that since it is increasing here, so since at least 20 dB is required, I should take n should be equal to 8. So, there should be 8 order here. This is a simple one, but you see this approximation of the function at higher values that will help us to find out what is the order of the filter. Next one, let us say that again another problem, that specification as maximally flat filter, low pass filter, omega c 2 gigahertz, load impedance 50 ohm and at least 15 dB insertion loss at 3 gigahertz. You see cutoff frequency 2 gigahertz, far away I want, because maybe at 3 gigahertz there is some interfering signal or another signal source is there. So, there I want to put it, at least you should have a high insertion loss of 15 dB there. Now, again the first thing is like before, also this is first we can find the order n by previous method, that PLR should be 1 plus omega by omega c whole to the power 2n. So, that is 10 to the power 15 dB. So, solving that n we are getting 4.22. So, we will take n to be greater than equal to 5. Now, let us take 5, and from 5 you can find the prototypes from Butterworth filter. See the table, for n is equal to 5, prototype values will be G1 is equal to 0.618, G2 is equal to 1.618, G3. This from the table directly, you need not find that this will be given in a problem, or as an engineer you can always refer to tables and find out what are the values. G6 is equal to 1.0. Now, you scale up, you know that from these values, the first value. So, I can draw that this will be the circuit, I have the source, then the source impedance that has been set to be 50 ohm. This is a Butterworth filter. So, our in prototype it is assumed as 1, that means G0 is always 1, but here it is 50. So, we need to scale with 50 at the appropriate time, that means our unknown value multiplier will be 50, and then we know the first element we can choose as L1. So, let me call L1, but since it will be scaled both in impedance, in frequency, type is same. So, no type change. So, I am calling it L1 dashed, then this will be C2 dashed, this will be L3 dashed, this will be C4 dashed, then this will be L5 dashed, then I need to stop, and the load impedance will be again RL is 50 ohm. So, what will be my value for L1 dashed? If you see your notes, this will be L1 unnaught omega c, and what is L1? L1 is nothing but your G1, that is 0.618. So, 0.618 into 50 by omega c, which is 2 pi into 2 into 10 to the power 10. So, this will give you a value of 2.46 nanohenry. Then C2 dashed will be C2 by R naught omega c. Now, C2 you can see that it will be 1.618 from the table, 1.618 by 50 into 2 pi into 2 into 10 to the power 9 is equal to 2.575 picofarad. Similarly, I think now you can go on your own. L3 dashed, you will get the value 7.958 nanohenry. C4 dashed will be 2.575 picofarad, and L5 dashed is equal to 2.459 nanohenry. So, this is an example of a prototype filter design, but we also scaled up. Prototype was first from the table, we could have found the prototype, but now we have scaled up in impedance and frequency. Now, we will see a type change type of thing. So, our third problem is this, that design a band pass filter having a 0.5 dB equal ripple response. It is given that you take n is equal to 3, the center frequency, that means our W naught is 1 gigahertz, bandwidth, percentage bandwidth is 10%, and impedance level is 50 ohm. So, we can, you see n is equal to 3 is said. So, basically we will have how many, the 4 things from table, G naught always is 1. So, what value, okay. So, I can take the circuit as like this. First element, if I take L1 dashed, second, because this is band pass, so I know any L1 is basically L1 C1 dashed, then L2 is L2 dashed C2 dashed, then L3 dashed C3 dashed, and that 3 n is equal to 3, finally it will be terminated by 50 ohm. Now, where from I get all these L1 C1 values? From the, it is equal ripple. So, Chebyshev, so I see Chebyshev with n is equal to 3, I get G1 is equal to 1.5963, that is L1 of the prototype, G2 that is 1.0967 is equal to C2, G3 is 1.5963 again from the table, L3, and G4, remember it is Chebyshev with n odd. So, no problem, G4 will be 1, and that is nothing but your RL. Now, you can easily find out L1 dash C1 dash from L1. What is that? Acha, before that, what is the delta value? Delta they said 10%, that means 0.1. So, what is my L1 dashed? L1 dashed is L1 Z naught by omega naught delta. So, it is L1, I have seen 1.5963, 1.5963 into 50 divided by 2 pi into 10 to the power 9 into 0.1, and that becomes 127 nanohenry. LC1 dashed, again it will depend on L1. The formula is delta by omega naught L1 Z naught. So, that you can put, and it will be 0.199 picofarad. L2 dashed again is delta Z naught by omega naught C2, and that will be 0.726 nanohenry, and C2 dashed will be C2 by delta omega naught Z naught, and that will be 34.91 picofarad. Similarly, L3 dashed, it will be same as this, 127 nanohenry, and C3 dashed will be 0.199 picofarad. So, if you can plot this, you can plot this attenuation. Obviously, that requires some computer programming, but this attenuation curve goes like this. This is 0.75, this is in gigahertz frequency, 0.75, 1.0, 1.25, roughly the curve is some ripple, but it comes to 1.25, and generally this ripple is around 0 dB approximately. So, this type of graph. So, this is a band pass, you see. Now, let us see another problem, that suppose that was I think 4. So, let us say 3, I think that band pass filter design we have seen. Now, implementation wise, you see that design, let us say low pass filter, cutoff frequency 4 gigahertz, third order equal ripple, that means Chebyshev with n is equal to 3, then impedance is 50 ohm, and pass band ripple is 3 dB. So, easily third order. So, we can find out the low pass prototype. So, here from table we can see from Chebyshev third order, again you see the final one RL should be 1. So, G1 is 3.3487, and that we can call L1. First one will take as L1, the series element, then G2 is 0.7117, let us call that C2. G3 from the table is 3.3487, and that we call L3, and G4 again I said Chebyshev with n odd third order. So, this is 1.0 and this is RL. So, let me draw the circuit, that this is one prototype, then this is my L1, this is my C2, and this is my L3, and then I have this as 1. Good. This is prototype, LPF prototype. Now, from this, these are all lumped elements. I know the values, but I need to do Richards transformation. So, I need to put those Richards transformation value. If you do that, then Richards transformation will look like this. Please see your notes that this first one is an L1. So, that is a series stub. So, I will have a series stub, this is a series stub and that is L1. So, I have to short it. So, what will be the value? You see, that time we said that this L will be the characteristic impedance, the length of the stub will be unit length lambda by 8. So, that we are calling that this characteristic impedance, let me write like this, that this is Z naught is equal to 3.3487 and this length is L. Then we will go, the C2 we will have to put, C2 is a shunt. So, we will have to put a shunt stub with open circuit and this L again will be that same lambda by 8 at the cutoff frequency, that means lambda by 8 at 4 gigahertz. So, what is the value of L? L is what is 4 gigahertz, lambda is equal to 30 by 4 centimeter, that is 7.5 centimeter. So, L is equal to lambda by 8 is 9275 probably, if I am correct, centimeter, or you can say 9.275 millimeter. So, all these lengths are this, and what is the characteristic impedance of this? C2, that this is G2, C2 value is 0.7117, we will have to take the inverse of that. So, that will become Z naught is 1.405. After C2, I have a series stub. So, we will have a series stub and then shorted because it is an inductance. So, and then from there this is a resistance 1 ohm. So, what is this value again? Let me say that this is L and this Z naught is 3.3487. So, now this is after recharge transformation. Now, if it can be implemented, okay, but if we think that okay, why don't have uniform type of shunt things, because making shunt stubs are easier than making series stubs. So, if we want to do that, you see that series stub was where in Kuroda's identity, I do not know whether I have notes. Yes. So, see Kuroda's identities. So, series stub I want to make shunt stub. So, Kuroda's second identity I will use. So, using Kuroda's second identity, so let me write applying Kuroda's second identity. This new circuit becomes very systematic procedure, this thing. So, instead of this I will make a shunt stub, then again already there was this one, So, then so what we have done, that here we have put, because after the stub, if you see the second identity, that you put a unit element and then your stub. So, that means, sorry, here actually let me redraw, because the element should be drawn first. So, first we will have to make one unit element, and then that element will be having a thing. Then we will have our original L1, then again we will put another unit element, and then we will close that. So, you see this is 50 ohm, these are all, now I will say L lengths, all are L lengths. L is lambda by 8. So, there are 3 such, and this is also a length L, unit length, this is also unit length L. So, all lengths are L, only they differ by their characteristic impedance. So, the first one Z naught, you see that what happens to n square is 1 plus Z2 by Z1, and you see our Z1, our, where is our Z1? Our Z1 was 3.3487. So, 1 plus Z2 is 1 and Z 3.3487, that gives this ratio as 1.299. So, with this first one will have a characteristic impedance of 1.299. Then this one, if you do that Z naught for this unit element, that will be with that ratio of 4.35. Then this one is Z naught is equal to 1.405, and this one is Z naught is equal to 4.35, and this one is Z naught is equal to 1.299. This is just, this is the original capacitor. So, that you see that is why this is different, but these two are same. Now, you can have this, instead of this 1 ohm, I have the impedance label as 50 ohm. So, 50 this was 1 ohm. Now, I need to scale up to 50 ohm. So, all these values I will scale up, and I will write this is 50 ohm. Then I will have this stub length again L, and Z naught is this 64.9 ohm, just scale up by 50 into this. Then I will have again this is of length L, length L, and this is Z naught is 70.3 ohm, 1.4 into 50. Then you go another, here there was one L, and this L has a Z naught of 217 4.35. So, 217.5 ohm. Then here again, this is L, and again the Z naught is 7.3. L will be from here, that from here to here there will be another line, and there the length is L and Z naught is 217.5 ohm, another unit cell. Then we have that and from here another stub. So, that again is length L, this length L, and this stub will have Z naught is equal to 64.9 ohm, and then you will have this 50 ohm line. Okay. So, you see I have now 3 these stubs, and also for unit cell 2 unit cells stub, but they are not stub, they are transmission lines. These 3 are 3 open circuited stub. This is for the first inductance, this is for the capacitance, this is for the inductance L3, and these are unit cells. So, now with these lengths the sizes are manageable. I have separated them. Now, these unit cells are called redundant sections, they are matched. So, that is why they are, because their impedances are both sides, they are matched to 1, that is why they do not disturb the operation of the filter, but what they do, they become separates the 2. So, that 2 stub elements there is enough separation between them. So, that any in the discontinuity, any high evanescent modes that gets generated, that can be tackled there, particularly at higher microwave frequencies. If any in discontinuities at those points there is any other modes generated, that comes, because this we are implementing by transmission line, but in other microwave filters we need to do it by waveguides, etc. There that type of problem may come. So, this completes the microwave filter design. Hope from the very basic point of filters, just from RC filter we have started, then we have seen that we need to have LC filters for radio frequencies, because RC filters are lossy. So, we intend to lossless LC filters. There we have seen how to design from image impedance concept. Then we came to the concept of characteristic impedance. We said that our network will be symmetric, we will have instead of 2 image impedances, 1 characteristic impedance. That characteristic impedance we tried to control, but we saw that there are a lot of problems of impedance matching, etc., that can be tackled. But another viewpoint is, if we tackle the insertion loss, if we specify the insertion loss of the whole filter, then we can synthesize any desired insertion loss characteristic, and by that we have seen first we need to do a low pass prototype filter design, and once we have low pass filter design, we can scale it up either in impedance or in frequency or in type. We can change the type and we can have any desired type of filters with any desired A. Then we have seen that if we want to implement it as high frequency or microwave type of filter, then we need to implement not through lumped circuit elements, but distributed circuit elements. So, how to do that? We have seen through Richards transformation, you can do that distributed transmission line implementation, and then to have some realizable gaps or to convert one stub to another, how to do that. So, for that we have introduced 4 Kuroda's identities. Any identity you need to choose for your particular application and you apply. The method is straightforward. It can be also easily implemented on a computer and you can do the whole things in your thing. That type of simulators etc. are available. You can use that, but once you know the basic principle design, then you use that, then it becomes meaningful. Otherwise, you won't be understanding what is happening, what is the principle, microwave principles from which this is there. So, we hope that with this you have got a thorough knowledge of microwave filter, both its design and implementation. Also, you will be able to analyze any filter design from this viewpoint. After this, we will switch over to another very important microwave circuit thing, that is amplifier. It will be an active based device design. This is filter was passive, but microwave amplifiers, they will be active device based. We will see that in the rest of this lecture series. Thank you.